So this is antennas and propagation. Antennas are nothing but a bell. It resonates. It's exactly equivalent to a big chime that you hit and you get a single tone out of it. All antennas are resonant one frequency, unless it's a non-resonant antenna. But if it's cut to a certain length, it's resonant with that frequency. I have a father-in-law that fought in World War II. He was in New Guinea at an air base. And a plane came in, single engine, small plane, had a wire going from the tip of the vertical stabilizer back down the cockpit. He looked at it, measured it, and made a comment to one of the guys that was guarding the plane, because this was top secret stuff. And he said, I didn't know they were using 15 meters. He threw him in the break. That was secret. All he did was measure it and do the math, right? He did that in his head and figured out what the frequency was. Okay, and a half-wave antenna, good for 15 meters. That's easy. Well, it took him some explaining to get him out of the grid. So we're going to go through antennas and we'll talk about propagation. Propagation is how that signal from that antenna gets to the other side of the world. Or maybe just from here across the valley. There's propagation of VHF too. We don't think about that. We think about just line of sight stuff. But there's really a lot going on. Most of it is not line of sight. VHF propagation is all about reflected and refracted waves. So here we go. Okay, the antenna system. All it is facilitates the sending of your signal to some distant station. You've got the conducting parts of the antenna designed to radiate or receive the radio waves. That's what's connected to your coax. That's the driven element. The driven element supplied directly with power from the transmitter. Tests and matching equipment. We've all got matching testing equipment here, but it's a simple meter, simple forward meter. If you've got a meter that measures the power out, you're good.
Do you use that during testing, or can you leave it hooked up during the entire time?
You leave it, so most transceivers will have a forward power meter. Most of them also have an SWR meter built in, so it's taking the forward and reflected power, dividing one into the other, and getting SWR. So it allows you to monitor the antenna performance. You want to know that you're probably the SWR is below 2 to 1. If it's below 2 to 1, it'll work. It may be cutting back power some if you've got a transistorized transceiver, but below 2 to 1, you're okay. Above that, no. If you're 3 to 1 or above, you better be using a tuner or rematch the antenna. Now, the corona ball on top of the HF antenna reduces RF.
So do you see those very often, the corona balls? I don't know if I've ever seen one.
Yeah, pretty much. Now, at VHF, it's really not needed because we're using FM, where the corona prevents the static is on single sideband and AM radio. That's where you will notice it. So car antennas that used to use AM radio, they would always have a corona ball. Polarization, that's the orientation of the radiated electric field, and that's all determined by the position of the antenna. Okay, horizontal, electric field parallel to the surface, vertical, perpendicular to the Earth's surface. Pretty easy. Polarization is the same as orientation of the driven element. So when the antennas at opposite ends of a VHF or UHF line of sight link are not using the same polarization, the received signal strength is reduced. They don't tell you how much. It's a lot. If you've got a line of sight and one of your antennas is vertical and the other is horizontal, there's a 30 dB hit. I mean, it just about goes away. So, fortunately, most of the stuff we do, the signals are bouncing around and we've got reflected signals, and every time it reflects off a plane surface, it rotates 90 degrees. Every time, bang, 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 rotates, rotates, rotates. So you end up with a mix of signals coming in that are partly horizontal, partly vertical, somewhere halfway in between, and it almost doesn't matter that you've got your HT and it's tilted over.
Is sometimes weather conditions can change
Even
it?
weather conditions can do that, yeah. So if you're line of sight to the repeater or line of sight to somebody else, you want to have the antenna in the same orientation.
If you can barely hear somebody and you don't know what's going
Yeah,
on, try
try tilting it.
rotating your radio, because it might change the polarization to what's happening to you from a reflection somewhere.
Yep. Or you're in a hot spot or a dead spot. All right, radiation pattern. This is, they say, a graph of the signal strength, but it is the signal strength in every direction or at every vertical angle. As with pattern, shows a horizontal signal strength, and there's some illustrations in the next slide. Elevation pattern shows vertical signal strength.
Okay, azimuth is around this way.
Right.
Vertical is how what angle the thing is taken off.
And then there are lobes, regions where the antenna is radiating that pattern. So this is your main lobe from the transmitted antenna. This is the back of the antenna, and this would be where the antenna is pointing. We call this a cartoid pattern. This is a typical pattern for a 2-element beam. So I have one here. I built this for doing T-hunting. It's a simple coax right up to, this is the driven element. This is split up here, and the coax goes to one element, the other element. I've bent over the ends, both to make it fit in the car easier, just to keep people from getting poked. I can mount it if I need to, but it's an easy thing to move around. Because the pattern is like that, as a cartoid pattern, I'm not worried about getting a signal this way. I'm worried about canceling the signal this way. So I want to move around and find where that null is right there. That's a sharp null. And I can find where the signal is by finding the null.
Yeah, you turn around 180 degrees and
So sometimes it's not finding the highest signal, it's where you get the least signal that it's easier to pinpoint.
yeah, you can see that the largest portion of that pattern is almost 180 degrees of
Yeah.
signal strength gain. And so that doesn't really help you much as far as finding the direction. It's the null that works.
So I use the same kind of an antenna where I live as a beam because I'm way up at the other end of the valley. I'm on the other end of Ashland. And I can use a cartoid pattern like that because it covers the whole valley. There's nothing behind me except the pass. I can cover everything, hit the repeaters a little stronger, and not worry about what's behind me because there's nothing behind me going over the pass.
And a directional antenna, to get gain, you have to take it from somewhere.
Yeah,
So
we're taking it from the back.
we're taking it from the back and sending the signal out toward the front if you're using it on transmit. If you're trying to use it to find something, you use the null because that tells you what direction, where the back of the thing is.
An antenna also has a vertical elevation pattern. This might be for, say, a dipole antenna at half a wavelength. Some of the signal will be going up and some of the signal will be going out perpendicular to the length of the antenna. So the higher you go, the more gain you get low, close to the horizon, but you'll also get these lobes in there, and that's just the way the design works. It'll scatter.
It's magic, but that's
Yeah.
something you gotta
So
deal with.
you can get quite a bit of gain in one direction and sacrifice what's behind you.
So if you want to talk in every direction,
Just a vertical antenna radiates every direction.
it's all omnidirectional. So you need a separate antenna, or
Well, you can use a separate antenna. Everything has pluses and minuses. A vertical antenna will get you, omnidirectional. But you're going to pick up more noise, more static, and
And there's less gain.
and less gain. You're transmitting in all directions.
Well, we'll talk more about how you can get gain out of a vertical antenna. by lengthening it.
Well, and vertical antennas, this is a vertical antenna. Your car radio is probably a vertical antenna. Depending on where the antenna is mounted, you probably have some nulls and gains. But
So if you live by the pass and you have it facing this way, it's because you mainly want to talk
yes,
to people this way, but if you wanted to talk to California, then that's not going to work so well.
You'd have to turn the antenna. So
Okay.
you'd put a rotator on it.
Okay.
Yeah, I've got like a 7-element antenna that's on a rotator. When I point it north, I've got a bigger signal. I can go all the way up to Roseburg, up 2 meters. Turning it around doesn't really do much. The pass is too high. You'd have too much of an angle to get over, and I can't hear California.
Okay.
so we're talking about.
Okay, radiation patterns. We talked about the omnidirectional pattern and directional. And isotropic is a theoretical antenna. You see that name, isotropic, and you're talking about a point source. That's theoretical. It doesn't occur in reality. But they use it as a baseline for radiation gain. So it's used as a reference for antenna gain, but that's the only thing it's used for. Referenced as an isotropic radiator is expressed in dBi. Antennas are passive, so power in equals power out. Energy can be concentrated in one direction at the expense of another. It's just like squeezing something into a space, like you're squeezing foam or something. You can think of those analogies. Concentrating the signal in a specific direction is gain. Signal strength in that direction is increased for both receiving and transmitting. So it's exactly equal. If you're hearing a stronger signal, you'll know they're hearing your signal as strong. Okay, gain is specified in decibel with respect to an identified reference antenna. And you'll see advertising for an antenna with dBi as the reference. The antenna will say it's 2.5 dBi. Well, more likely you want, what's the reference to a regular half-wave dipole? That's dBd. Convert dBd, you add 2.5 dB. So an isotropic is 0, a standard 1-element energized dipole is 2.5 dB over an isotropic. Front to back ratio is the ratio of your signal in the front on a beam compared to the ratio in the back. So a dipole, there's no front to back. It's equivalent in both directions. But if you've got a 2-element beam, you might have quite a bit front to back. It might be as high as 20 dB. Antenna gain is stated in dBi compared to dBd for the same antenna, it would be 2.5 dB higher. So one's isotropic comparison, the other is compared to a dipole. Antenna advertisers like to advertise with the isotropic because it makes them look better. It's 2.15 dB higher. But that's sometimes, okay, you look at it and go,
That's a marketing thing.
you know, it's 3.2 dB. Well, that's only 1.1 dB better than a dipole. It's just not much. So this is kind of something we don't use very often. And link margins and budgets. The link budget is the sum of the transmit power and antenna gains minus the system losses. So what are they talking about there? So, okay, you've got 100 watts coming out of your transmitter, and you've got an antenna that's got a gain of 3 dB over a dipole. So you're getting some real gain over a dipole. But you've got 150 feet of coax. You've got some loss in that coax. And then you've got lightning arrestor in there. In fact, maybe you've got 2 lightning arrestors in there. Then you got a bulkhead going in through the wall. So you've got 2 connectors on each side of that. You've got a couple of jumpers inside because you're using a tuner. Okay, now you've got
Switch.
like 8 connectors. Each one of those is, maybe a quarter of a dB. Not much, but they add up, okay? So you take all of those losses, the length of the coax, the number of connectors you've got, maybe the tuner has its own losses, it does. So you have to take all of those together and subtract that from the gain of your antenna. Sometimes it washes out. I mean, the gain of your antenna and all the losses maybe is 0. Well, that doesn't help. But you need to know that. You need to be able to figure out what the losses are in a line. I had a system in Texas with 150 feet of coax underground, and a lot of, little things on each end. Your lightning arresters, I had 2 lightning arresters in there, and it made it difficult. I needed a gain antenna, and I needed it up high. But I put it on a tower, and it worked. But you try to minimize the number of connections and use the best connectors you can find. Don't screw around with cheap connectors in China. It'll bite you in the butt, I guarantee it. Okay, what happens when the antennas at opposite ends of the VHF, UHF line of sight link are not using the same polarization? What happens? One of them's vertical, one of them's horizontal. You lose a lot. You lose maybe 30 dB. So, it's up to 30 dB, depending on what other reflections
Okay.
and refractions.
Alpha
go on.
Bravo Charlie Delta.
So, modulation sidebands might become inverted, receive signal strength is reduced, signals have an echo effect, nothing significant will happen, its signal strength is reduced. What is antenna gain?
Charlie.
Okay? All right. Any questions? Yeah. And what is the purpose of the chronoball on an HF mobile antenna?
Delta.
Correct. What is a link budget? Alpha,
Charlie.
Yeah. That could be a little tricky. Go back again. The sum of antenna gains minus the system losses. That looks like a pretty decent definition, but the answer is sum of the transmit power and antenna gains minus the system losses as seen at the receiver. How does the antenna gain stated in dBi compare to the gain stated in dBd?
So I have a question.
Yeah.
So on my ICOM, when I'm tuning, I should be turning down my RF
Power.
radio frequency because of what you just said.
Your power setting. Turn it down to 10 watts.
So when I get my tuner, turn down the RF and then push
Yep.
tune.
And that'll prevent arcing in the tuner as well.
Okay.
So
So you-
which
You just
one?
turn the power down.
Alpha Bravo Charlie Delta.
Gain in dBi is 2.5 dB higher than gain in dBd.
Because you're asking us supposed to work higher at the
And
Again?
dBi is a theoretical.
Yeah, when you see the I, that means isotropic, and you see the D means dipole. So you're comparing isotropic to a dipole. The gain of the dipole is 2.5 dB higher than the isotropic. So if you're comparing antenna gain, it's the isotropic difference. that-
And if your antenna doesn't say I or D, just assume it's I. It's the marketing people are gonna try to push whatever is gonna sell their product. And, if it has a higher gain, it sounds like it's a better antenna. But if it doesn't say I or D, assume it's I.
What's meant by the terms dBi and dBd when referred to antenna? Okay, you just explained that. So which one is it? Alpha. Very good. Okay.